Projective geometry is a topic of mathematics. It is the study of geometric properties that are invariant with respect to projective transformations. This means that, compared to elementary geometry, projective geometry has a different setting, projective space, and a selective set of basic geometric concepts. The basic intuitions are that projective space has more points than Euclidean space, for a given dimension, and that geometric transformations are permitted that transform the extra points to Euclidean points, and vice versa. Properties meaningful for projective geometry are respected by this new idea of transformation, which is more radical in its effects than expressible by a transformation matrix and translations. The first issue for geometers is what kind of geometry is adequate for a novel situation. It is not possible to refer to angles in projective geometry as it is in Euclidean geometry, because angle is an example of a concept not invariant with respect to projective transformations, as is seen in perspective drawing. One source for projective geometry was indeed the theory of perspective. Another difference from elementary geometry is the way in which parallel lines can be said to meet in a point at infinity, once the concept is translated into projective geometry's terms. Again, this notion has an intuitive basis, such as railway tracks meeting at the horizon in a perspective drawing. See projective plane for the basics of projective geometry in 2 dimensions. While the ideas were available earlier, projective geometry was mainly a development of the 19th century. This included the theory of complex projective space, the coordinates used being complex numbers. Several major types of more abstract mathematics were based on projective geometry. It was also a subject with a large number of practitioners for its own sake, as synthetic geometry. Another topic that developed from axiomatic studies of projective geometry is finite geometry. The topic of projective geometry is itself now divided into many research subtopics, 2 examples of which are projective algebraic geometry and projective differential geometry. Overview. Projective geometry is an elementary non-metrical form of geometry, meaning that it is not based on a concept of distance. In 2 dimensions it begins with the study of configurations of points and lines. That there is indeed some geometric interest in this sparse setting was seen as projective geometry was developed by Desargues and others in their exploration of the principles of perspective art. In higher dimensional spaces there are considered hyperplanes, and other linear subspaces, which exhibit the principle of duality. The simplest illustration of duality is in the projective plane, where the statements 2 distinct points determine a unique line, and 2 distinct lines determine a unique point show the same structure as propositions. Projective geometry can also be seen as a geometry of constructions with a straight edge alone. Since projective geometry excludes compass constructions, there are no circles, no angles, no measurements, no parallels, and no concept of intermediacy. It was realized that the theorems that do apply to projective geometry are simpler statements. For example, the different conic sections are all equivalent in projective geometry, and some theorems about circles can be considered as special cases of these general theorems. During the early 19th century, the work of Jean-Victor Poncelet, Lazare Carnot and others established projective geometry as an independent field of mathematics. Its rigorous foundations were addressed by Carl von Staudt and perfected by Italians Giuseppe Pino, Mario Pieri, Alessandro Padua and Gino Fano during the late 19th century. Projective geometry, like affine and Euclidean geometry, can also be developed from the Erlangen program of Felix Klein. Projective geometry is characterized by invariance under transformations of the projective group. After much work on the very large number of theorems in the subject, therefore, the basics of projective geometry became understood. The incidence structure and the cross ratio are fundamental invariants under projective transformations. Projective geometry can be modeled by the affine plane plus a line at infinity, and then treating that line as ordinary. An algebraic model for doing projective geometry in the style of analytic geometry is given by homogeneous coordinates. On the other hand, axiomatic studies revealed the existence of non-Desarguesian planes, examples to show that the axioms of incidence can be modeled by structures not accessible to reasoning through homogeneous coordinate systems. In a foundational sense, projective geometry and ordered geometry are elementary since they involve a minimum of axioms and either can be used as the foundation for affine and Euclidean geometry. Projective geometry is not ordered, and so it is a distinct foundation for geometry. History. The first geometrical properties of a projective nature were discovered during the 3rd century by Pappus of Alexandria. Filippo Brunelleschi started investigating the geometry of perspective during 1425. Johannes Kepler and Gar copyright Desargues independently developed the concept of the point at infinity. Desargues developed an alternative way of constructing perspective drawings by generalizing the use of vanishing points to include the case when these are infinitely far away. He made Euclidean geometry, where parallel lines are truly parallel, into a special case of an all-encompassing geometric system. Desargues' study on conic sections drew the attention of 16-year-old Blaise Pascal and helped him formulate Pascal's theorem. The works of Gaspard Monge at the end of 18th and beginning of 19th century were important for the subsequent development of projective geometry. The work of Desargues was ignored until Michel Chasles chanced upon a handwritten copy during 1845. Meanwhile, Jean-Victor Poncelet had published the foundational treatise on projective geometry during 1822. Poncelet separated the projective properties of objects in individual class and establishing a relationship between metric and projective properties. The non-Euclidean geometries discovered soon thereafter were eventually demonstrated to have models, such as the Klein model of hyperbolic space, relating to projective geometry. This early 19th century projective geometry was intermediate from analytic geometry to algebraic geometry. When treated in terms of homogeneous coordinates, projective geometry seems like an extension or technical improvement of the use of coordinates to reduce geometric problems to algebra, an extension reducing the number of special cases. The detailed study of quadrics and the line geometry of Julius Pla 1/4 CK still form a rich set of examples for geometers working with more general concepts. The work of Poncelet, Jacob Steiner and others was not intended to extend analytic geometry. Techniques were supposed to be synthetic, in effect projective space as now understood was to be introduced axiomatically. As a result, reformulating early work in projective geometry so that it satisfies current standards of rigor can be somewhat difficult. Even in the case of the projective plane alone, the axiomatic approach can result in models not describable via linear algebra. This period in geometry was overtaken by research on the general algebraic curve by Kleb, Riemann, Max Noether and others, which stretched existing techniques, and then by invariant theory. Towards the end of the century, the Italian school of algebraic geometry broke out of the traditional subject matter into an area demanding deeper techniques. During the later part of the 19th century, the detailed study of projective geometry became less fashionable, although the literature is voluminous. Some important work was done in enumerative geometry in particular, by Schubert, that is now considered as anticipating the theory of Chern classes, taken as representing the algebraic topology of Grassmannians. Paul Dirac studied projective geometry and used it as a basis for developing his concepts of quantum mechanics, although his published results were always in algebraic form. See a blog article referring to an article and a book on this subject, also to a talk Dirac gave to a general audience during 1972 in Boston about projective geometry, without specifics as to its application in his physics. Description: projective geometry is less restrictive than either Euclidean geometry or affine geometry. It is an intrinsically non-metrical geometry, whose facts are independent of any metric structure. Under the projective transformations, the incidence structure and the relation of projective harmonic conjugates are preserved. A projective range is the one-dimensional foundation. Projective geometry formalizes one of the central principles of perspective art, that parallel lines meet at infinity, and therefore are drawn that way. In essence, a projective geometry may be thought of as an extension of Euclidean geometry in which the direction of each line is subsumed within the line as an extra point, and in which a horizon of directions corresponding to coplanar lines is regarded as a line. Thus, two parallel lines meet on a horizon line in virtue of their possessing the same direction. Idealized directions are referred to as points at infinity, while idealized horizons are referred to as lines at infinity. In turn, all these lines lie in the plane at infinity. However, infinity is a metric concept, so a purely projective geometry does not single out any points, lines or plane in this regard. Those at infinity are treated just like any others. Because a Euclidean geometry is contained within a projective geometry, with projective geometry having a simpler foundation, general results in Euclidean geometry may be derived in a more transparent manner, where separate but similar theorems of Euclidean geometry may be handled collectively within the framework of projective geometry. For example, parallel and non-parallel lines need not be treated as separate cases. We single out some arbitrary projective plane as the ideal plane and locate it at infinity using homogeneous coordinates. Additional properties of fundamental importance include Desargues' theorem and the theorem of Pappus. In projective spaces of dimension 3 or greater there is a construction that allows one to prove Desargues' theorem. But for dimension 2, it must be separately postulated. Using Desargues' theorem, combined with the other axioms, it is possible to define the basic operations of arithmetic, geometrically. The resulting operations satisfy the axioms of a field except that the commutativity of multiplication requires Pappus's Hexagon Theorem. As a result, the points of each line are in one-to-one correspondence with a given field, F, supplemented by an additional element, A, such that Ra equals a, AA equals a, R plus A equals a, R/0 equals a, RA equals 0, AAR equals Ra equals A. However, 0/0, a plus a, AAA, 0A and A0 remain undefined. Projective geometry also includes a full theory of conic sections, a subject already very well developed in Euclidean geometry. There are advantages in being able to think of a hyperbola and an ellipse as distinguished only by the way the hyperbola lies across the line at infinity, and that a parabola is distinguished only by being tangent to the same line. The whole family of circles can be considered as conics passing through two given points on the line at infinity at the cost of requiring complex coordinates. Since coordinates are not synthetic, one replaces them by fixing a line and 2 points on it, and considering the linear system of all conics passing through those points as the basic object of study. This method proved very attractive to talented geometers, and the topic was studied thoroughly. An example of this method is the multi-volume treatise by H. F. Baker. There are many projective geometries, which may be divided into discrete and continuous. A discrete geometry comprises a set of points, which may or may not be finite in number, while a continuous geometry has infinitely many points with no gaps in between. The only projective geometry of dimension 0 is a single point. A projective geometry of dimension 1 consists of a single line containing at least 3 points. The geometric construction of arithmetic operations cannot be performed in either of these cases. For dimension 2, there is a rich structure in virtue of the absence of Desargues' theorem. According to Greenberg and others, the simplest two-dimensional projective geometry is the Fano plane, which has 3 points on every line, with 7 points and 7 lines in all, having the following linearities. With homogeneous coordinates A equals, B equals, C equals, D equals, E equals, F equals, G equals, or, in affine coordinates, A equals, B equals, C equals, D equals, E equals, F equals and G equals. The affine coordinates in a Desarguesian plane for the points designated to be the points at infinity can be defined in several other ways. In standard notation, a finite projective geometry is written Pg, A, B, where A is the projective dimension, and B is 1 less than the number of points on a line. Thus, the example having only 7 points is written Pg, 2, 2. The term projective geometry is used sometimes to indicate the generalized underlying abstract geometry, and sometimes to indicate a particular geometry of wide interest, such as the metric geometry of flat space which we analyze through the use of homogeneous coordinates, and in which Euclidean geometry may be embedded. The fundamental property that singles out all projective geometries is the elliptic incidence property that any two distinct lines L and M in the projective plane intersect at exactly one point P. The special case in analytic geometry of parallel lines is subsumed in the smoother form of a line at infinity on which P lies. The line at infinity is thus a line like any other in the theory. It is in no way special or distinguished. The parallel properties of elliptic, Euclidean and hyperbolic geometries contrast as follows. The parallel property of elliptic geometry is the key idea that leads to the principle of projective duality, possibly the most important property that all projective geometries have in common. Duality. In 1825, Joseph Jurgen noted the principle of duality characterizing projective plane geometry. Given any theorem or definition of that geometry, substituting point for line, line for pass-through, collinear for concurrent, intersection for join, or vice versa, results in another theorem or valid definition, the dual of the first. Similarly, in three dimensions, the duality relation holds between points and planes, allowing any theorem to be transformed by swapping point and plane, is contained by and contains. More generally, for projective spaces of dimension n, there is a duality between the subspaces of dimension n and dimension r1. For n equals 2, this specializes to the most commonly known form of duality that between points and lines. The duality principle was also discovered independently by Jean-Victor Poncelet. To establish duality only requires establishing theorems which are the dual versions of the axioms for the dimension in question. Thus, for three-dimensional spaces, one needs to show that every point lies in three distinct planes, every two planes intersect in a unique line and a dual version of to the effect, if the intersection of plane P and Q is coplanar with the intersection of planar and S, then so are the respective intersections of planes P and R, Q and S. In practice, the principle of duality allows us to set up a dual correspondence between two geometric constructions. The most famous of these is the polarity or reciprocity of two figures in a conic curve or a quadric surface. A commonplace example is found in the reciprocation of a symmetrical polyhedron in a concentric sphere to obtain the dual polyhedron. Axioms of projective geometry. Any given geometry may be deduced from an appropriate set of axioms. Projective geometries are characterized by the elliptic parallel axiom, that any two planes always meet in just one line, or in the plane, any two lines always meet in just one point. In other words, there are no such things as parallel lines or planes in projective geometry. Many alternative sets of axioms for projective geometry have been proposed. Whitehead's axioms equals, these axioms are based on Whitehead, the axioms of projective geometry. There are two types, points and lines, and one incidence relation between points and lines. The three axioms are, G1, every line contains at least 3 points, G2, every 2 points, A and B, lie on a unique line, AB. G3, if lines AB and CD intersect, then so do lines AC and BD. The reason each line is assumed to contain at least 3 points is to eliminate some degenerate cases. The spaces satisfying these three axioms either have at most one line, or are projective spaces of some dimension over a division ring, or are non-de Sargesian planes. One can add further axioms restricting the dimension or the coordinate ring. For example, Coxeter's projective geometry, references Veblen in the three axioms above, together with a further 5 axioms that make the dimension 3 and the coordinate ring a commutative field of characteristic not 2. Axioms using a ternary relation equals, one can pursue axiomatization by postulating a ternary relation, ABC, to denote when 3 points are collinear. An axiomatization may be written down in terms of this relation as well, CO, ABA, C1, if A and B are 2 points such that, ABC and, ABD then, BDC, C2, if A and B are 2 points then there is a third point C such that, ABC, C3, if A and C are 2 points, B and E also, with, BCE, ADE but not, ABE then there is a point F such that, ACF and, BDF. For 2 different points, A and B, the line AB is defined as consisting of all points C for which, ABC. The axioms CO and C1 then provide a formalization of G2. C2 for G1 and C3 for G3. The concept of line generalizes to planes and higher dimensional subspaces. A subspace, AB XY, may thus be recursively defined in terms of the subspace AB X as that containing all the points of all lines YZ, as Z ranges over AB X. Collinearity then generalizes to the relation of independence. A set B, Z of points is independent, AB Z, if B, Z is a minimal generating subset for the subspace AB Z. The projective axioms may be supplemented by further axioms postulating limits on the dimension of the space. The minimum dimension is determined by the existence of an independent set of the required size. For the lowest dimensions, the relevant conditions may be stated in equivalent form as follows. A projective space is of L1, at least dimension 0 if it has at least one point, L2, at least dimension 1 if it has at least two distinct points, L3, at least dimension 2 if it has at least three non-collinear points, L4, at least dimension 3 if it has at least four non-coplanar points. The maximum dimension may also be determined in a similar fashion. For the lowest dimensions, they take on the following forms. A projective space is of M1, at most dimension 0 if it has no more than one point, M2, at most dimension 1 if it has no more than one line, M3, at most dimension 2 if it has no more than one plane, and so on. It is a general theorem that all coplanar lines intersect. The very principle projective geometry was originally intended to embody. Therefore, property may be equivalently stated that all lines intersect one another. It is generally assumed that projective spaces are of at least dimension 2. In some cases, if the focus is on projective planes, a variant of M3 may be postulated. The axioms of, for instance, include and. Axiom becomes vacuously true under and is therefore not needed in this context. Axioms for projective planes equals. In incidence geometry, most authors give a treatment that embraces the Fano plane PG, 2, as the minimal finite projective plane. An axiom system that achieves this is as follows: P1, any two distinct points lie on a unique line. P2, any two distinct lines meet in a unique point. P3, there exist at least 4 points of which no three are collinear. Coxeter's Introduction to Geometry gives a list of 5 axioms for a more restrictive concept of a projective plane attributed to Bachmann, adding Pappus's theorem to the list of axioms above and excluding projective planes over fields of characteristic 2. The restricted planes given in this manner more closely resemble the real projective plane. See also. Notes. References. External links: Projective Geometry for Machine Vision, a Euro tutorial by Joe Mundy and Andrew Zisserman. Notes based on Coxeter's The Real Projective Plane. Projective Geometry for Image Analysis, a Euro free tutorial by Roger Moo and Bill Triggs. Projective Geometry, a Euro free tutorial by Tom Davis. The Grassmann Method in Projective Geometry, a compilation of 3 notes by Biroli 40 on the application of exterior algebra to projective geometry. See Biroli 40, Introduction to Differential Geometry, following the method of H. Grassmann, E. General Theory of Rectilinear Ray Systems, M. Pash, on the focal surfaces of ray systems and the singularity surfaces of complexes.